Hey guys, in this video what I'm going to be doing is showing you how to solve a conservation of momentum problem. So here's the problem. Let's say that we've got this green ball which is initially stationary, and let's say it's about to be collided with this blue ball which is traveling upwards at 6 meters per second, and it's traveling upwards according to this dotted line which I drew just here. Okay, and we also know a little bit more information. We know that their radiuses are the same, so R1 is equal to R2, which I'll just call R, and their masses are also the same. M1 is equal to M2, which I'll just call M, and perhaps most importantly, we're given that the coefficient of restitution is 0.6. Okay, and from all this information, what I want you to do is I want you to find out what the final velocity of our first ball is, V1 dash, and also our final velocity of our second ball, V2 dash. I want you to find these for me. Pause the video, have a shot at it now, and come back when you're done, and you'll see how you did compared to how I am about to go. Okay, well, in order to do this, what we need to do is we need to draw what they look like during collision, or just before collision, I should say. Alright, well, this is what they look like. This is the green ball just here. This is the white dotted line which I drew, which describes the path of the blue ball. And it looks just like this when they just start colliding. It'll look just like this. Done. Okay, now if we wanted to get an understanding of the angle at which they collide, let's connect their center of masses just here and draw a line together. Okay, fortunately for us, because their radiuses are the same, we know that this right here is just going to be 2r. Also, because the blue ball has a radius r, we know that this distance is just going to be r. Meaning that if I were to define theta to be this angle just here, we could calculate it based off trigonometry by completing this right angle triangle. So we know using trigonometry, cosine of theta is just going to be equal to adjacent over hypotenuse, which is r over 2r. The r's cancel out, bam, bam, and you're left with cosine theta is equal to a half. You can solve this and show that theta is equal to 60 degrees. That's going to be useful. Okay, what was the point in all that? The point in all that was so we can now start having a really good understanding of our tangential and normal directions. Remember, this is our tangential direction just here, which is tangential to the collision, and n, which I'm going to define in this direction just here, is just going to be, as you've guessed it, normal to our collision. So this is it. Well, it's in the direction of our collision, sorry. Okay, well, let's see if we can actually start redescribing our velocity vector of our first ball in terms of n and t. Remember, our first ball was just traveling at 6 meters per second upwards, or in the positive j direction. If we were to describe it in normal and tangential components, it would look like this. This is going to be the normal component, and this will be what looks like the tangential component. And of course, this makes a right angle triangle. Not only that, but we know that this angle here is going to be 60 degrees. We just shown that, which means that we know this angle here is 30 degrees because this forms a right angle triangle, meaning that we can quantify what the lengths of these vectors are, and we know that this is going to be 6 sine 30, and this is going to be 6 cosine 30. So if we were to start tabulating our results, this is what it would look like. So here I've created a table which shows all the velocities of our balls before and afterwards, and I've split them into both the normal and tangential components. Right? So we just figured out that for the first ball, the blue ball, V1t is just going to be equal to, let's see, it'll be 6 sine 30. If I zoom up, that's this one. It's going to be 6 sine 30 because it's in the positive tangential direction. That's why it's positive just here. And in the normal direction, it'll be 6 cosine of 30. I hope that makes sense. Okay, now what about the green ball, our second ball? At its initial condition, or just before collision, what is its velocity? Well, it's 0, right? Which means that if you split it into normal and tangential components, it's also 0. Easy enough. I should mention all these units are in meters per second as well. Now here's the problem. We've got 4 unknowns just here, and we need to solve for these somehow. How do we solve for them? Well, we start with the conservation of momentum. I almost forgot the name of it. The well-anticipated conservation of momentum. So let's start with the conservation of momentum in the n direction. Let's do conservation of momentum in the n direction. Okay, all that means, it sounds fancy, but all that really means is that you get your mass and you times it by the velocity of your first block in the normal direction, and then you get your mass and you times it by the velocity of your second block in your n direction, and you know that's just going to be equal to the total momentum of your objects after collision, which is just going to be, because they separate ways, it's just going to be mv1n dash plus mv2n dash. I hope that makes sense. Basically, momentum before equals momentum afterwards in the n direction. Okay, because all the masses are constant and the same, they're shared, that means we can easily divide by m for both sides, and what we're left with is v1n plus v2n is going to be equal to v1n dash plus v2n dash. This is going to be useful. We're going to be using that soon. We can't use it now because there's two unknowns in one equation, but we'll be solving that soon by introducing something called the coefficient of restitution E, which was 0.6. Now, I've shown in a previous video that the coefficient of restitution is v2n dash minus v1n dash, all divided by v1n minus v2n. Oh, not dash, just v2n. Okay, so what we're going to do now, this is our second equation. We need to solve these simultaneously in order to find for our velocities of our first ball and our second ball after the collision. So if you could hazard a guess, how would you think would be the best way to solve for this? Well, we know that v2n is just going to be equal to 0, so that's a good start. We know that the initial velocity of our second ball is 0. So you're probably guessing that the easiest way to solve for this is to multiply v1n by both sides for our second equation. So let's simplify the second equation just here, and what we're left with is v1n times by e is going to be equal to v2n dash minus v1n dash. Okay, so that's our second equation, a little bit more simplified. Now what can you think is the best way to do this? Well, notice on the right-hand side of our first equation, we've got v2n dash plus v1n. If we just add both of these simultaneous equations, we'll eliminate one of the variables we need to solve for. So let's add equation 1 and let's add equation 2. And what we're left with is, I want to keep everything in one picture, it's going to be v1n e plus the left-hand side of this, which is going to be v1n plus v2n, and that's going to be equal to, let's see, the right-hand side has some cancellation. It's going to be 2v2n dash and plus 0, right? Because this is a minus and this is a minus. Basically, these cancel out when you add them. Bam, bam. Okay, we can simplify this a little bit more, knowing that v2n is actually going to be equal to 0, right? And we're left with v2n dash v2n dash is going to be equal to v1n times by e plus v1n all divided by 2. And when you plug that into your calculator, you are going to be left with 4.16 meters per second. So that's 4.16 meters per second. So let's write that up here in our table where we can actually keep track of this. This is going to be v2n dash 4.16 meters per second. So far, so good. Okay, so we've applied two equations and we've still got a few equations left. How do we approach this from here? Well, we know we can actually plug this back in to solve for our tangential component. So we can plug v2n dash is equal to 4.16 back into equation 1, and what do we get? Well, we get 1.04 meters per second. That is going to be equal to v1n dash. That is our velocity of our first ball in the normal direction after collision. Okay, so I should specify this is going to be v2n dash right here. Okay, so let's write that above, where we can keep track of all this. This is going to be 1.04 meters per second. Okay, cool. Now let's see if we can solve for v1t dash and v2t dash. Now we're at crossroads. We could actually do the conservation of momentum in the t direction if we wanted to, but there's an easier way. In fact, not just an easier way, there's a more crucial way. We know that during collision, these two balls actually do not exert forces on each other in the tangential direction. Right? Basically, the forces they exert on each other are purely in the normal direction. And so, if either ball does not have a force being exerted on it in the tangential direction. So none of this, they don't have a force in the tangential direction during collision. That means that their momentum for each ball is conserved in the tangential direction. So that means, I hope I'm not losing you, that means that the momentum for ball 1 in the tangential direction, so in t direction, is conserved. Right? So what that means is you can write mv1t is actually going to be equal to mv1t dash. That's all it means. That just means that the momentum is conserved for each individual ball in the tangential direction, right? That's what we can say. And of course, these masses are the same, so we can cancel them off, meaning that v1t is actually just going to be equal to v1t dash, right? That's because no forces are acting on either ball in the tangential direction during collision. Likewise, we could say the exact same. Momentum before collision is conserved in the t direction for the second ball, before in t direction. So in other words, we can say mv2t is going to be equal to mv2t dash. Cancel off the m's, bam, bam, and what we're left with is v2t is going to be equal to v2t dash. Bam, beautiful. So let's scroll up to see if we can fill this in. We know that, whoops, too far. We know that this right here must be equal to 0 because the tangential component momentum is conserved, and likewise we know this is just going to be 6 sine 30. I'll evaluate that soon. Okay, so once we evaluate that, this is what we're left with. Alright, I've just evaluated each of the individual values which I had in here. This turns into 3, this turns into 5.2, and now we're ready to solve the final parts of this problem. To do this, let me actually scroll just to the right just a little bit. Okay, so this is all we need right now. We know all the components of the velocities of each of the ball in the tangential and normal directions. So let's see if we can use this to find the final velocities of our first ball. Basically, what is v1 dash? What is that? Well, we're only asked to find the speeds. We're not asked to find the directions, so that makes this problem easier. We know that v1 dash is going to be equal to the square root of v1t squared plus v1n squared after their collision. So v1t dash, v1n dash, right? And we also know that v2 dash, basically the magnitude of your velocity after collision, is going to be equal to the square root of v2t dash squared plus v2n dash squared. All right? I hope you can understand why it's going to be square rooted. That's using Pythagoras. Essentially, if you've got a magnitude of your velocity just here, say this is your coordinate system just here, you could break it into its components, x and y, say, and of course you just use Pythagoras to find out the length of that vector. So that's where the square root sign comes in. And when you plug that into your calculator, what you're left with is the velocity of our first ball after collision is just going to be 3.17 meters per second. Remember, we're asking for a speed, not the velocity, so just the magnitude of the vector is fine. And for our second ball after collision, the velocity is 4.16 meters per second. Okay guys, I hope that makes sense. This is how you apply these formulas in these types of problems.